I want you guys to know that coffee is an important tool used by planetary scientists to investigate the surfaces of other worlds. Without this tool, we'd be nowhere. Okay, good morning, Astronomy 1010. Welcome to what is now our third lecture on planetary geology. In particular, we're dealing with the terrestrial planets. And it's quite a big subject. So we've had a lecture last week, a lecture on Monday, and this will be the final lecture, and we'll try to transition into a separate discussion of planetary atmospheres. When we last left off in our last episode, we were learning about the 4 geological processes. Do you guys remember what those 4 geological processes are? Because they're kind of a big deal for our homework today. They're a big deal in the test. Most of the questions.
I found them. So erosion, impact craters, plate tectonics. Forgot what the other ones were.
There's only one more left. So you said erosion, you said impact cratering, you said plate tectonics, and volcanism, volcanoes, right? So last class, I introduced the concept of the 4 geological processes, and I said they're the kind of big deal in planetary geology. When we look at the surface of a planet, like last time, last time we looked at this planetary surface. Do you guys recognize this planetary surface here?
Mars.
Yeah, you can tell it's Mars because the giant Valles Marineris, the massive volcanoes on the Tharsis Montes plain, and the intense heavy bombardment cratering that covers the southern hemisphere of the planet. When we look at the surface of a planet, it's kind of like a murder mystery or the board game Clue or a Sherlock Holmes story. There's a scene here. Something happened, we weren't present for it, and we, the planetary scientists, the people who are curious about other planets, are trying to deduce or infer what might have happened. And just like in Clue, you've got a number of options. You've got Professor Plum in the library with the candlestick. The options that we usually have are, was this an example of impact cratering? Was this an example of volcanism? Was this an example of some kind of tectonic activity? Or was this an example of erosion? And it can be a confusing scene because sometimes it's multiple things together that are woven together in a complex way. However, up to now, I mostly talked to you guys about impact cratering. And today I'd like to say a few words, not a ton, but a few words about volcanism, tectonics, and erosion. Now, I'm going to end off on erosion because it turns out to really fully appreciate how erosion changes a surface, you really need to start discussing planetary atmospheres. And I've got to tell you, the atmospheres of planets are a whole nother level of complexity that require their own separate sort of investigation or lecturing on. So why don't we get started with volcanism, and let's think about what we know about it. Let's cut through the cratering here. I really like to start with this picture when we consider volcanism. This is a picture of the Cleveland volcano, I believe in Washington. Yes, in Washington. And there's an eruption going on that's being photographed from the International Space Station from 400 kilometers above. And what's amazing about this photograph is it's a good reminder to the new student that volcanoes don't just produce lava, which is what we tend to think of when we think of volcanic eruptions. We think of lava bursting out of the caldera of a volcano. Volcanism also produces gas, large quantities of gas. And from the point of view of planetary science, this might actually be the more important issue, although both play a role in shaping a planet. So perhaps what we could do is we could, this Pintabo volcano in the Philippines, when it erupts, it produces massive mushroom clouds of gas. And if you've ever seen the videos of people on ferries watching this thing go off, it's pretty terrifying and also majestic at the same time. Maybe what we ought to do is just kind of start with a little diagram of a volcano. And honestly, the one on Wikipedia is pretty good. Volcano Wiki. We're not going to label all the parts, but there's a couple of terms that we might want to use here. And at some point, I just need to steal this this cross section here and put it into my slideshow. So you'll notice they have a number of different classic parts of a volcano labeled, but why don't we just focus on a couple of them, okay? So we'll kind of reproduce a little diagram like this. And if you guys have that up on your own computers, you can help fact check me. Let's go into note-taking mode here. And let's do a little tidbit on volcanism. Okay, so the first point I made is from the point of view of planetary science. We're interested in volcanism for two reasons in which it changes a planet. It produces lava, and lava is a liquefied form of basaltic rock. We're going to talk about that in a moment.
It just got really bright. Oh, there we go.
I think this has an auto contrast feature. Can you read it? That's what matters.
Now I could read it.
Okay.
It was just, oh no.
And lava plays the role of it repaves surfaces. So when we look in the Tharsis Montes region of Mars, you'll remember that surrounding those volcanoes, there were very few impact craters and the terrain was very smooth. So that's one thing that volcanism changes about a planetary surface. The other thing is what we call outgassing. Outgassing is when volcanoes produce planetary atmosphere gases, okay? Outgassing is responsible for not only the formation of an atmosphere, but the maintenance of an atmosphere. So they contribute to atmospheres. You know, when Earth first formed 4.6 billion years ago, there was no atmosphere on Earth. And even if there was, it certainly was not made of oxygen and nitrogen like it is today. That built up over billions of years through constant outgassing. And probably the rate at which volcanoes erupted was greater in the past than today, because as you remember, planets start off with more interior heat, okay? Volcanism is ultimately caused by having a hot and especially convective interior on Earth. Our asthenosphere, or our mantle, is the convective rock layer, which can kind of erupt or break through the surface through what we would call either cracks or vents in the lithosphere. Which you remember is kind of like the crust, but it's in terms of rigidity, okay? So let's make a really quick and somewhat crappy diagram of not every volcano, but what a typical volcano might look like, okay? So not all volcanoes have this, but this structure here, this is called the dome. It's going to turn out that not all forms of volcanism form a dome, but in general, we think of a dome when we think of volcanoes. This opening is called the caldera, okay? And then there's something called a vent or a flute. Let's see what they call it here. So, oh, they're calling it a throat, okay. And so the idea is that you'll have some kind of a channel through which the warm and somewhat molten rock is going to be pushed up to the surface. Somewhere down here, you'll have a magma chamber. There are sometimes side vents. You guys remember that at the end of our lab last week, we could see that there were these collapsed lava tubes on the slope of Arcia Mons. And those were caused by eruptions that burst out of the side of a volcano. So this might be considered a side vent. You have a magma chamber. This structure here is the channel that leads down through the lithosphere into the warm convective rock of the asthenosphere. And so I suppose we could call that you know, the vent or the crack or whatever. So we'll call this a vent. This might be called the up here the throat. Okay. So once this volcano, so what happens is, I want you guys to remember that when
You're throwing up? Is that?
well,
an example?
before the volcano vomits up its guts, if you want to put it that way, when the material is down here, it is not in the liquid phase. Remember that this material here is warm convective plastic or solid rock. It's like silly putty. It's rock that flows. The reason why this stuff is not lava is because it's under way too much pressure. Remember, you've got the pressure of hundreds of kilometers of rock sitting on top of you. And remember, if I showed you that phase diagram with water, how it only turns into solid, liquid, and gas at sea level pressure? At certain pressures, water will always be in the form of ice. And this rock is under so much pressure that it's basically in a solid form. As the warm rock is pushed up through cracks in the lithosphere, the pressure on the rock becomes reduced, and it suddenly can become liquefied into sort of a molten lava. And then it starts to build up into these magma chambers. Also, keep in mind that what's warming the rock is the lightest density materials, which is water and CO2. They are kind of heating up the rock. It's almost like steam is heating up the rock and they're melting it. And then eventually you form this big bubble of a magma chamber. It builds up tons of pressure under all that steam and CO2. And then at some point it just bursts through the rock. And as soon as that magma hits the surface, it suddenly goes from being under thousands of pounds of, well, I guess if we want to do it in kilopascals, more than hundreds of kilopascals of pressure to suddenly 1 kilopascal or 1 atmosphere pressure, and it just liquefies and it flows as lava across the surface. I'm just trying to point out that the lava only becomes liquidy once it gets up through the volcano. I think that's an important thing to think about. That's how it's building up this pressure here. Let's make a note about planetary gases too. So I'm going to put the arrow for caldera down here. And I want to draw some plumes of gas coming out. And why don't we list some of the common gases? I guess I'm going to have to make some real estate here, guys. I'm sorry. The common gases that come out of volcanoes are carbon dioxide, that's one, CO2, water, H2O. Literally, probably most of our oceans came from eruptions of volcanoes taking place over hundreds of millions and even billions of years. Part of the air we breathe is diatomic nitrogen. We see that being produced in volcanoes on Earth as well as Mars and Venus. There's probably a bit of methane, although these are the most important gases. Oh, another important gas that comes from volcanism, SO2, is called sulfur dioxide. These are sometimes referred to as volatiles. These are molecules which would prefer to be in a gaseous form at Earth-like temperatures and Earth-like pressures. But carbon dioxide, water, and nitrogen, those are the big ones, okay? Okay, the things that I want to talk about before I show you some pictures are, there are 3 types of volcanoes that can form on planets. It depends on the quality of the basaltic rock. And there's also kind of 2 different scenarios of volcano formation. So let's borrow a little bit from our slideshow. And let's, it looks like I'm doing the formation first. Let's do the 3 types of volcanoes. I'm gonna mix this thing up here. So here's a piece of frozen lava, slide 58. Once lava cools and solidifies, it becomes a type of rock called basalt. It's a sort of dense but porous rock. Most of the surfaces of the terrestrial planets are covered in basaltic rock. For instance, the composition of the moon, especially those lunar maria, you remember those big smooth gray maria that we saw in our moon lab? All basaltic rock. Surface of Venus, basaltic rock. Most of Mars, basaltic rock, and Earth too, although Earth does have some granite along the continents. Now, if I was a geologist, I would probably wax philosophical with you guys about the different compositions, the chemical compositions of basalt from different volcanoes around the world. Since I'm a little bit more of an astronomer, I kind of squint and wave my hands a bit. But let's just look at 2 different compositions of basalt so we can kind of understand and see what makes geologists stay up at night, okay? These are 2 different types of volcanoes. Hawaii is going to be called a shield volcano, whereas Mount St. Helens would be considered a strato volcano. And I want you to notice at first blush that basalt is basically made of the same minerals, right? You guys will remember that does anyone remember the definition of a rock? What's the definition of a rock? Did we learn anything about that?
Isn't it like a compound of minerals?
That's it. An aggregate of minerals would be a nice way to say it, but what you said was cool too. So here you can see the different minerals that are making up basalt. Now, from our point of view in planetary science, here's my first blush takeaway. The primary mineral is silicon dioxide. You'll remember I told you that's why we call planetary rocks silicates. Silicates are things like silicon dioxide. Notice that the second and tertiary ingredients are, I don't know exactly how a geologist would say this or a chemist, but it looks like dialuminum trioxide. This is ferrous oxide. This is 2 aluminums stuck to 3 oxygens, 1 iron stuck to 1 oxygen, 1 magnesium. So it's like a metal connected to a rock, a metal connected to a rock. Silicon's not a metal, but okay. But so you've got your silicon dioxide, and then you've got these more metallic minerals. Basically, the most abundant mineral for both types of basalt is silicon dioxide. The second most abundant is aluminum oxides. The third most abundant is iron oxides. But notice the ratios differ. Here, there's a smaller, shallower percentage of silicates than there is in the Strato Volcano. And this change in the amount of silicon dioxide, I believe, is what affects the viscosity of the lava. Do you guys know what that term means, viscosity?
Like how thick it is?
Well, you could say thick, but it's really about flow, Jake. It's the resistance to flow. So for instance, Jake, I would say that honey has a high viscosity, and I would say that soy sauce has a low viscosity. Does that make sense? I could see why you thought of it as thickness, but I think that the proper way to say it is
Yeah.
flowiness, okay? Now, this percentage of silicon dioxide will affect the viscosity of the lava, and that in turn will affect what type of volcano the planet will form. So for instance, I want to backtrack here. Here's a picture of some low viscosity lava. This lava can run for literally hundreds of miles in a liquid state before it finally cools down into solid rock. You guys will notice that it's warm and glowing. It's basically functioning like a black body. In order to give off visible light that we can see with our eyes, your temperature has to at least be, I don't know, 1,000 Kelvin at least, or something like that. Maybe less than that, but you know, upwards of 500 Kelvin probably. Look at that compared to this. This would be an example of a more high viscosity lava. You change the percentage of silicon dioxide and it gets to be more like honey and less like soy sauce. And that's going to determine what types of volcanoes we can form. That's our next set of notes, is the 3 types of volcanoes, so that we're going to recognize them as we look around different planets. Then we'll talk about how they form. Okay. So there are sort of 3 sort of types of volcano that we see around the different terrestrial planets, okay? And it depends upon the viscosity of the basalt. The first type doesn't even seem to you to be like a volcano. It doesn't have a dome. And these are called volcanic plains. Volcanic plains are made of low viscosity basalt. The basalt can flow for so many kilometers that it does not build up a dome, and it ends up just kind of forming basically what you would think of as a pool of lava. And examples of these types of volcanic plains would be the Lunar Maria. On Earth, we find it in the form of the Yellowstone caldera. Yellowstone National Monument is basically one big giant volcanic caldera that does not have a dome. So Yellowstone would be an example on Earth. On Mars, the Planitia that you saw last time would be examples of this. Let's just take a quick look. Unfortunately, I have not gotten to show you guys the moon through the telescope because of COVID-19. But I swear, when you look through the moon through a telescope with your eyes and you see the Maria, you can really tell that these Maria kind of look like frozen pancake batter. This picture doesn't even do justice to how cool it looks when you're looking at it with your eye. You can see where the lava was kind of flowing and then kind of just solidified into these clumps of mountains and things. And some of them are quite smooth. The moon is nice, of course, because there's nothing else to distract you from the rock itself. So you can really just kind of examine these volcanic plains. The second type of volcano is made from a medium viscosity lava. And this creates actually the tallest types of volcanoes. Here you can see an aerial image of Olympus Mons, the shield volcano on Mars. Made from medium viscosity lava, okay? And shield volcanoes, because the lava, they do form a dome, but they tend to be gently sloped but very tall, okay? These are the tallest volcanoes. In the case of Olympus Mons, 27 kilometers tall. So examples here would be Olympus Mons, Mauna Kea on Hawaii, the main volcano on Hawaii, is an example of a shield volcano. So we see these on Earth. Lastly, the third type of volcano is from the thickest lava. It does not form the tallest volcanoes, but it does form the pointiest volcanoes. And when we think of a volcano like Mount St. Helens or something, at least if I was a kid with a box of crayons, I probably would have drawn a Strato Volcano as a tall, sharp, and pointy volcano. They're not as tall as Olympus Mons, but they have a very steep peak to them. And these are our Strato Volcanoes. These are, of course, made of high viscosity lava. Basically, the lava doesn't flow very far before it cools. And so that tends to kind of build up your classic short and pointy shape, right? And examples of this would be Mount St. Helens, and we see them on Venus. There's even one or two on Mars, but Venus has a lot of them. Venus has a volcano called, I think it's called Mat Mons. Mat Mons. Am I spelling that right? Is it two A's or two T's? I don't think it's Matt like math is.
I can't.
You can't read that?
Yeah, I can't see the other thing.
Too small?
No, your head was just in the way.
Oh. I'm not spelling that right. We can only see Mat Mons using radar imaging. My head was in the way because I was going to try to show you a picture or reconstruction of this thing. Hold on, let my head be in the way for just a moment here.
It's MAAT.
Thank you. I thought as much. Here's a reconstruction of what it looks like. This is not an optical image. This is not a picture taken at visible wavelengths, but this is a radar or radio image that's been three-dimensionally reconstructed. This is the tallest volcano on Venus. There's a lot of debate over whether it's active or not. Most people think that Venus's volcanoes should be active because Venus should have a thin lithosphere. But direct evidence is hard to come by, so people debate it in the scientific literature. Thanks for fact checking that, Matt. Okay. So now you'll recognize the three different types of volcanism we see around planets. After this, we're going to talk about how they form. There's kind of two different scenarios for the formation of volcanoes. I'm just giving you guys a moment to kind of catch up. Andrew, why don't you let me know when you're finished copying here, okay?
Okay.
I'll sip some coffee. I'm very pleased with this.
All right, I'm all set.
Okay. I'm gonna, all right, for the memory books. I'm going to erase. Any objections? Okay, so there's probably more than two formation scenarios, but two different scenarios come to mind when we form volcanoes. So two formation scenarios. And these are worth mentioning because they both kind of tie into the underlying geology of a planet, okay? So first, let's talk about something called a convective hot spot. The idea behind a convective hot spot is you have some piece of lithosphere, okay? So this here is your lithosphere. And the lithosphere is sitting on top of a convecting mantle or a convecting asthenosphere. And what you have are these warm plumes of rock that constantly push up at the same location of the planet. So basically, they call this a convective upwelling, meaning you're always the bubbles of the lava lamp are always pushing up there. So this is convective, I hear geologists say this, upwelling, or a convective plume. Sometimes they'll call it a mantle plume. And the mantle plumes just keep kind of pushing up on the same region of the lithosphere. And this tends to cause the lithosphere stress. Eventually, you force the lighter density materials up into this vent or crack, and that begins to form a volcano. I think nowhere can this be seen better than that image that we looked at last time. Let's go to my labs here. Remember that when we looked at the Mars topographical map, we could see such a mantle plume in the high elevation areas surrounding the major volcanoes of Mars. So let me go to the hand tool here. Let's kind of keep zooming in. You know, I once asked one of my geologist colleagues what they thought of this map of the surface of Mars. And my friend Emily, who's a geologist, had just had a really cool way of looking at it. She said, Brendan, look at all of this rock, this high elevation rock concentrated in one area with all these volcanoes. You can see on Mars, this is where convection just kept pushing up and pushing up and pushing up at the surface of Mars. In fact, there's so much convective upwelling, it probably caused enough stress on Mars's lithosphere to actually start to split and crack the lithosphere apart and form this channel here. And all of these volcanoes are located in the same region because this is just one big mantle plume that just keeps pushing up and stressing the surface of Mars. Now remember that Earth has plate tectonics. So on Earth, this lithosphere is in motion, unlike it is on the other planets. So what that means is convective hotspots, when they form volcanism, they can tend to form these kind of island chains or archipelagos, one example of which is Hawaii. So let me just get back to the pictures here and see if I can show you two different images from two slideshows. So here's a sort of diagram of our convective upwelling, slide 52. The convective mantle just keeps pushing up on a region of lithosphere. Stresses cause cracks and channels to form, which then fill up with light density, warm, buoyant rock, which eventually liquefies and causes pressure. And the other picture I want you to think about here is a picture from my Earth slideshow showing you the Hawaiian Archipelago, which we believe is over a convective upwelling on Earth. 29. You can radioactive date the rocks on the islands of Hawaii, and you quickly discover that the further they get from the main island, the older the rock is. So this graph shows us ages of the islands in millions of years. We have about 5. Now, does anyone familiar? My geography kind of stinks here. This is the main island of Hawaii, and I should really get some help here. The names of the other islands are Oahu and, well, in any case, sorry about my Hawaiian geography. I've never been to Hawaii before. This island here is maybe 5 million years old. This island is maybe 2 or 3 million years old. maybe 2 million, maybe 1 million, and then 500,000 for the main island of Hawaii. So what's happening is each time the crust sits over the convective upwelling, it pushes up on Earth and it forms a volcano, causes eruptions, which builds up the dome. Then the dome slides off of the convective hotspot. And friends, they're also showing you elevation here. This is elevation according to color. So red is the tallest elevation, green has the lowest elevation. What do you think is wearing down the elevations of these volcanoes as they move off the convective hotspot?
The erosion.
That's right. We're seeing the effect of 3 different geological processes at work. We're seeing volcanism build up the domes. We're seeing plate tectonics slide the domes off the hotspot. And then we're watching as erosion wears them down. Now, it's not in this picture, but way the hell up off of to the left here is a much older island called the Midway Atoll, which is famous for that World War II battle, the Battle of Midway. Do you guys know about the Midway Atoll? Have you ever seen a picture of it? It's literally a buried volcano, and you can still see the caldera. Most of it's underwater today because of erosion. It's been washed back down to the sea, but can you guys see this? This is the caldera of what was once a mighty volcano. Erosion has washed it back down into the sea, and the only bit of the atoll which still sticks above the surface of the water is this little military base here, which is kind of wild, right? But if you look at an aerial photograph, you can still see the caldera under the water. You want to know what else is creepy? There is a new volcano. Basically, the main island of Hawaii is kind of half moved off the hotspot. And today there is a new volcano forming in the island, in the Hawaiian Archipelago. It's called Lohi, Future Volcanic Island. Let's see if I spelled that right. The Lohi Seamount is currently forming underneath the ocean and is getting ready to rear its head above the water. Let's see if we can get to the wiki page here. Yeah, so here we can see the formation. Oh, sorry, this is what it looks. So this is the main island of Hawaii with Mauna Kea and Mauna Loa. And Lohi is forming there, negative 980 meters. Give this thing, 10,000, 100,000 years, and it's going to start to push its way up out of the Pacific Ocean, ready for us to put condos and beach resorts on, or whatever we have to do to inhabit this thing. I also want to show you guys pictures of it forming. Don't forget that, oops, sorry, that's not what I meant to do.
Professor, can I interrupt you?
Yes, sure.
So I took Emily's class before, the
Yes.
geology, and she actually showed us Google Maps, and she zoomed out where you could actually follow the chain of extinct volcanoes, which then became seamounts. You could follow the chain from Hawaii all the way up to Alaska, as the plate shifted over the hot spot. So you can actually just zoom out and see them.
Wait, who am I talking to right now?
All the way to the tip of Alaska. This is Andy.
Oh, hey, Andy. Yeah. And remember, Andy, if you've taken a couple of geology courses, you may know just as much geology as me, because, like I said, I'm more of an astronomer. The deeper we get into geology, the more uncomfortable I get. But that is a cool. So what? I probably need a different version, like the satellite version, right? So, oh wow, look at this.
Yeah,
hey, Andrew, this is such a great contribution. Thank you so much for telling us about that. So look, so let's see here. Here's the main island of Hawaii. Look, there you can see Lohi forming off the coast. And look at that, huh? You can follow that volcanic chain. There's the Midway Atoll. And look, you're right, it keeps going all the way out to here, huh? Does that get to the Aleutian Islands of what? Oops, sorry. So my resolution is, oh yeah, but look, I can see what you're talking about, Andrew. They're going all the way out here. You can see these, and actually they do kind of, these are the Aleutian Islands, which are another set of volcanoes. So as Earth's plate tectonics are pushing these things around, you can see the volcanoes moving around Earth. What a cool contribution. Thank you so much for, I forget to use Google Maps as much as the geologists do. That is a great tool for us to consider there. Very cool. Okay, so now you guys get the idea about the convective hotspot. Let's also talk about one of the other formation, which is also deeply connected to geology and plate tectonics. And this second one happens mostly on Earth. This is where we have what's called a subduction zone. Keep those contributions coming, Andy, if you have any more tidbits like that. So the subduction zone is where you have a piece of Earth's lithospheric crust being forced underneath continental crust because of plate tectonics, and it triggers some volcanoes. So let's look over here. So let's first draw a piece of, this is what we would call seafloor crust. Seafloor crust is formed at these kind of underwater volcanoes called ridges, like the Mid-Atlantic Ridge, where we have convection basically pushing up on a kind of mini underwater volcano. And you don't really form too much of a dome. You form a small ridge, but you're basically pushing warm convective rock up through a vent that then forms new pieces of the seafloor crust. And it kind of pushes the entire seafloor away, spreading out from this vent. Eventually, the seafloor crust kind of pushes along until it comes into contact with some continental crust, okay? Now, the continental crust is low density, let's call it light but old. So the crust is lower density granite. It's like this stuff here. A lot of the continental crust is this granite, which Andrew and I were talking about last time. The seafloor crust is both dense but younger rock, because this rock recently formed from those convective bubbles that pushed up into the seafloor. And what do you think is going to happen when this dense rock hits this more buoyant rock? They're going to smash into each other, and the denser rock is going to sink underneath it. So this is what's called a subduction zone. Examples of subduction zones are like those deep trenches. You guys probably have heard of the Marianas Trench, that 7-kilometer deep trench that James Cameron explored with his like high-tech torpedo or human submersible, whatever you want to call it. As the heavy, denser crust gets forced into these subduction zones, remember that a lot of the crust of the seafloor is volcanic rock, but it's mixed in with coral rock, which is made of carbon dioxide, and it's bound up CO2 in there. All of those materials, when they get jammed into the warm, deep belly of Earth, they just start to melt and vaporize. And they vaporize and heat up the surrounding rock. And you guessed it, they start to trigger volcanoes. So suddenly you form these vents and magma chambers that are pushing up CO2 and water in a gaseous form, and you're melting the rock. And suddenly, pow, you've got some volcanoes which are going off along the coast surrounding these so-called subduction zones. And the subduction zones are triggers of volcanic formation. Andrew could probably contribute to this too. I'm sure Emily Burns told you about this. But there is a region of Earth. Let me get the picture here. Oh, here's a nice diagram of a subduction zone. But I was hoping that we could talk about the Ring of Fire together. Bear with me, guys. I keep losing my. I've got my slideshows are kind of broken into 2 different pieces here.
Professor.
Yeah.
I have my, this is Andy again. I have my geology book out. I do have some good pictures.
Well, we should share your screen. If we have to look at a book, that might be kind of awkward. I don't know if they're on your screen. That's okay. We got the internet. Unless you have something that I don't have, something that's, well, what do you got? Let's start there.
Hold on one second.
Here's the, you know me, I love the Wikipedia. I can't get enough of it. Here's the Wikipedia diagram of the Ring of Fire. And so if you look around Earth, most of the volcanic activity and most of the earthquake activity are not scattered randomly around Earth, but they're connected to these deep ocean trenches. And we found volcanoes all along the coast of South America, the west coast of the United States, right up to Mount St. Helens, the Aleutian Islands of Alaska. Think about all the earthquakes that happen in the Philippines, also the volcanic islands of Japan. Much of the Earth's volcanism is kind of working hand in hand. Here's the big message I'm trying to give away. On Earth, plate tectonics and volcanism are bound together. They are a symbiotic organism that trigger and support each other. We don't see that so much in other planets. In fact, here's the secret. There might be little tectonic cracks on Mars or little tectonic cracks on Venus, but Earth is the only planet with an active set of plate tectonics. And you can almost see, I'll come back to you in a second, Andy, but look again at this topographical map. Now that we've talked about that, what do you guys think about the fact that there are 3 major volcanoes in a row on Mars? Do you suspect that that's a random coincidence? What do you think of that? What's going on there?
It's probably a convective hotspot or a subduction zone.
Well, subduction zone, maybe not so much because we don't see, well, it's hard to say, but I think maybe you can, yes, it's more like a convective hotspot, but can you see that maybe Mars in the past actually tried to kickstart a tiny little bit of plate tectonics, and it was trying to push the lithosphere along the hotspot? But what happened on Mars to stop that process? Why didn't Mars develop a proper set of plate tectonics? Maybe we need a picture. Why didn't Mars develop a bona fide set of plate tectonics, and what does it have to do with slide 21? Why didn't Mars get to develop a full-blown set of plate tectonics?
Because it's technically almost like frozen. It wasn't really hot enough.
Yeah, I mean, in the past, it probably was warmer, right, Jake? But
Yeah.
now today, we can see its lithosphere extends so far deep down that Mars, having a smaller, remember, volume to surface area ratio, Mars was cooling at a much more rapid rate than Earth and Venus were. And as it cooled, its lithosphere thickened, and it kind of froze into place the kickstart of plate tectonics. Now, Andrew, what pictures were you thinking about sharing with us? Because if you think it's going to help here, we could even share your. Well, first of all, Andrew, you're not even sharing your face. Oh, there you are. Okay. So what do you got? Okay, let's.
There.
Oh yeah, that's a lovely diagram.
Sure.
That's a lovely diagram of a convection zone. That looks good, buddy. I can see that here. So there's
the
your
the
seafloor spreading, and then we can see the.
And there's these.
That's actually a pretty nice diagram. I like that. How was that class, by the way? Was that good? Did you learn a lot?
Yeah, I love this class.
If you were out there collecting samples of granite in the Midwest in your RV there, then you clearly got the bug. That was good.
I do have a few samples of scoria. It's like pumice. It's volcanic rock. It just shows how many holes it's nothing impressive.
I mean, it's so impressive for me. Like I said, the more I learn about geology, the more I realize what a cool science it is, especially because as an astronomer, I'm used to only imagining the things that I spend all my time talking about. It's not like I can reach out and touch Betelgeuse. But a geologist can take a walk through the Lincoln Woods or something and pick up samples of the stuff that they study. And I'm very envious that they get to touch the things that they spend this time thinking about. I think that's very cool. Okay, let's push on. Let's talk a little bit about plate tectonics. And because we've been already kind of talking about it. Can I erase? Andrew, do you need a
Yeah.
second? Okay.
No, you could erase. It's fine.
Okay, I'm going to try to say something confusing here. Let's talk about plate tectonics. And the first thing that I want to say, I'll put it in dazzling blue here, is that a full-blown, robust set of plate tectonics is unique to Earth. But what is unique to Earth would be sort of a full active surface of plate tectonics. A full active, let's just call it a program, because I don't know what else to say. A full active program of plate tectonics. We certainly see tectonic microfeatures on other planets. And you can usually tell the difference between tectonics and, say, erosion. Remember last time, guys, I had that high resolution image of, okay, what was it called? It was the Valles Marineris. And I had this picture up here, this very high resolution. Ooh, come on. Oh, I want to show you this one because the contrast is a little easier to see. This is going to take a second to load here. This might actually be too, oh, come on. Oh, here we go. I believe this is worth it. I hope this is worth it. Maybe I can close a couple of other tabs here. I can feel my computer starting to choke here. Oh, man. What? Oh, there we go. Okay. Do you guys see, I really want to point some stuff out here. Can you guys see surrounding the Valles Marineris these hard jagged cracks? Now, Mars never developed a full set of plate tectonics, but when I see these hard kind of jagged looking things that look like a broken egg or a broken vase, these to me seem like tectonic features. Probably the splitting apart of Mars's crust and the pushing up against it, these created these violent stresses which shattered and compressed the lithosphere of Mars. When I see hard, jagged, crispy features like that, I tend to think this is a tectonic feature. So I want to be careful to say that it's not like you won't find tectonics anywhere but Earth. If you look over here, you can see tectonic stresses there and there. Hell, even if we look at that nice high resolution image of our Siamons,
Professor, it could also be glacial scarring too.
well, not on Mars. Not on Mars. Well, now that you say that, I'm less sure of myself, but I don't think there was ever the same amount of, Mars today has an active amount of wind erosion, but if there was glaciers moving across the surface of Mars, I guess now that I think about it, it could be possible, but I doubt it. If I had to put my money down on one roulette number versus another, I would say that those were tectonic stresses formed by the splitting apart of the Valles Marineris. But like I said,
Putting a guess in, yeah.
Mars definitely has ice caps, which is why your idea is not crazy. And I'd have to think about it. You know, it could be that you've got something there, but Do you guys see these features here? Actually, I don't know if you ever learned about this in your geology class. Can you guys see how there are these ridges that go up and down and up and down? I think they refer to these in geology as a Horst-Graben combination. And I'm just showing you a couple of examples of tectonics. Horst-Graben. Let me see if I got that right. A Horst and Graben, these are geological regions where faults and stresses on the lithosphere of the planet can form these kind of choppy blocks that punch up and punch down along the surface of the planet. Doesn't this remind you of that here when you look at those features? Now, if you were to say, well, what if the 4 geological processes cause this? Obviously, it's a big fucking volcano. There's not too many secrets there. But notice that even though it's a volcano, it formed tectonic-like features along the edge. So sometimes the closer you look into things, the more there's kind of overlap in the 4G. It's not like they compartmentalize and it's only volcanism or it's only tectonics. These things can kind of get mixed up together. But however, that being said, the only planet which has a robust full set of plate tectonics is Earth. Only Earth has the combination of thin lithosphere, convection, and one other secret thing that I don't want to tell you just yet, okay? So let's take a look at our so-called conveyor belt model of plate tectonics. So in plate tectonics, we need to have a thin lithosphere. And the thin lithosphere floats on a convective warm layer of rock called the asthenosphere. So this is the convective asthenosphere. Now, convection is going to push along the lithosphere and drive it forward on what some scientists refer to as the conveyor belt model. Typically, the velocity with which these plates are pushed are somewhere between 1 to 3 centimeters per year. That doesn't sound very fast. That's the rate at which your fingernails grow. But Earth doesn't evolve geologically over years or tens of years. It evolves dynamically over hundreds of millions of years. Over hundreds of millions of years, this stuff can add up. There's a reason why the continents of Earth look like a giant jigsaw puzzle with South America fitting like a puzzle piece into the continent of Africa. These two things are probably connected, and seafloor spreading has been driving them apart over 100 million years or so. So the lithosphere is pushed by convection in the conveyor belt model or the conveyor belt analogy. The consequence of plate tectonics, of which there are many, is this is related to the formation. It forms continents. You guys saw in a previous lecture that you could tell Earth was Earth just by seeing the continents on there. It forms mountain ranges. Basically, if you see mountains on another planet, that means that planet has plate tectonics. If you see continents on another planet, that planet has plate tectonics. It also forms sort of separations between continents, sometimes called rift valleys. Oh, not to mention, as those lithospheric plates push against each other, it's responsible for earthquakes, which we got to experience a magnitude 4 earthquake in Rhode Island here about a week ago, and several of you said you felt it. I sure did. One of the first ways that, we need to take another important note here, and I'll show this to you. Earth's lithosphere is fractured. This is a key thing. It can't just be a lithosphere. It's got to be thin enough so that the lithospheres form cracks and fractures. Earth's lithosphere is broken or fractured into a set of approximately 10, we call them lithospheric plates. It is the lithospheric plates that float on the convective asthenosphere. That float on. I'm just going to cheat here, and I'm going to write convective mantle because I'm feeling lazy and it's hard to write at the bottom of my screen or the bottom of my whiteboard. Class, if you plotted the points of all the earthquakes that happened in the last 50 or 100 years, you would naively expect the earthquakes to be randomly distributed all over the earth with no rhyme or reason. But guess what you would discover? It's not random. Here's an excellent figure. This slide here shows you green dots wherever there was an earthquake in the last 100 years. And notice that rather than being randomly distributed across the earth, they perfectly outline the boundaries of those 10 lithospheric plates that I showed you. Let's also take a notice that plate tectonics does not mean continents floating on the ocean. I don't want you to think that continents are some kind of a rubber raft. The North American plate consists of the continent of North America plus the seafloor plate below the Atlantic Ocean. So this is a contiguous plate rather, right? Notice that we do occasionally get the odd earthquake in the Rhode Island area, but as the book is fond of pointing out, us in New England, we are sitting on some of the oldest continental crust on planet Earth. Because we are so far away from the boundaries of these plates, the last time this bit of continent had to bash against another piece of plate was so many hundreds of millions of years ago that we're basically on a pretty tectonically inactive region of the world. If we lived out in LA, we'd have to have our buildings kind of earthquake proof. On the other hand, one of the reasons why that 4.0 earthquake was so scary to us is because earthquakes are usually not something designers think about in Rhode Island because they're so infrequent. Even a slight earthquake like a magnitude 5, I mean, I felt my bed rocking around back and forth because I'm on the top of a brick building. Could you imagine if it was a magnitude 5 or 6 earthquake? There is a finite possibility that my whole building could have collapsed on my head and you guys wouldn't have had to listen to these lectures anymore, okay? So that's, you know, buildings have to be designed earthquake proof out in Los Angeles because of the frequency. And the architects who designed many of the buildings and homes we live in did not think about those things. That makes us actually kind of more vulnerable in a way. I have one more point to make, and it's a very important point. I want to see if you guys can figure it out. There is one thing that all of these lithospheric boundaries have in common. The boundaries of the lithospheres are not that random. They're always located where?
On the west.
Not on the west. This is the east, right? Here's some boundaries in the east. It's not an east versus west thing. It's a
circle, sort of. Motion.
The circle binds the, wait, what did you just say?
It's like a circle motion.
It's something else. Where do all of these boundaries take place?
In the ocean.
That's right. Do you notice that none of these seem to slice through the middle of a continent? Okay, the only place is maybe Iceland. You can actually see the mid-Atlantic ridge through a part of Iceland. You can walk through it. But with the exception of Iceland and a little bit of stuff over here, for the most part, they're always in water. And you know, We believe this is a key necessary ingredient. Think about it. Water kind of lubricates and chips away rock. Think about the Colorado River carving out the Grand Canyon. You know, if we have like rock, paper, scissors, water beats rock if you give it enough time. And why I think this is important is, remember, students, that Venus has an equally thin lithosphere as Earth does. You can see in this diagram that Venus and Earth are sister planets. Venus certainly has volcanoes on its surface. We just saw Matt Mons. And even though Venus has volcanoes, we believe that Venus has no plate tectonics, despite having a wicked thin lithosphere. In fact, if you look at those pictures of the planets shown by their continents, F5, this is Earth. There you can see all the continents formed by the bashing of plate tectonics, right? And now look at Venus. Despite being a sister planet, there's like hardly any continental land masses at all. The idea of why that is even though Venus has a thin lithosphere, it's so stupid hot on Venus that Venus baked away all of its water maybe 1 billion years ago in a complex process you'll learn about next week. Venus has no water on the surface, no moisture in the atmosphere. There is no water on that entire planet. In fact, the cloud layers are so thick and so hostile and so hot and under so much pressure, you couldn't even stand in a spacesuit on the surface of Venus. I think the pressure of their atmosphere is hundreds of times greater than ours. You would just get your ass crushed like a tin can by gas, not even by rock. Because Venus is such a hostile environment, there were several programs in the 80s to land a spacecraft pioneered by the Russians. They were called the Venera space missions. And the Russians tried over and over again to land a spacecraft on Venus. And every time the spacecraft descended, acid rain clouds would melt away the metal and the atmospheric pressure would just crush the spacecraft. I think they threw 12 spacecraft down into the clouds of Venus before one, or two actually, finally landed at the surface for 5 minutes before disintegrating. Would you guys like to see the pictures? Hell yes, you would. And I have them in my slide show for you. So this will be a fun way to end our lecture for the day. Something to think about. Well, we have to talk really quick about erosion, but I'll make that brief.
Oh wait, I need the other notes too. Like
I'll let you grab those before we move on, Andy. But so I don't lose I don't want to forget to come back to this. Okay. So here, let me just do this here, like 3-second picture show. Slide 122 is a picture of Venus seen from above. The yellowish clouds are actually, the yellow color isn't due to carbon dioxide, it's due to some trace elements. But those are thick clouds of carbon dioxide. I mean, hundreds of times more gas than you have on Earth. Now, let me show you a picture of the Russian spacecraft. I love this photo. It looks so late 70s, early 80s. There you can see the Venera 12 or 13 mission. You've got the main mothership there, and there's a little pod that's going to descend from the bottom of it. I like those old school, like Soviet computer screens and stuff. It just looks awesome in that space. Anyways, so the artist illustration of the way it works is they sent that spacecraft to Venus, dropped a little shielded pod down that had a parachute, actually made it to the surface, took 2 photos, and then it died. Okay, this was by the way, this today is still 2020, the only 2 spacecraft that have made it to the surface. And we know less about Venus than we do, I don't know, about Pluto, if you think about it, which is crazy. Okay, here's one photograph the moment it landed. Now, do you guys see this? This is the metal cap covering the camera. It's the lens cap that popped off, and you can see it melting and disintegrating in the caustic Venus atmosphere. You can even see the spacecraft itself, the metal melting and disintegrating as it sits there. And what do you see next to it? Just slabs of dry, hot, probably gooey volcanic rock. And they reconstructed some 3D pictures. This is our idea of what a day on Venus looks like. It's the most hostile planetary surface in the entire solar system. Just slabs of basaltic volcanic rock, thick stagnant clouds of atmosphere. They probably had to take this picture at infrared wavelengths so they could even see, because I think the clouds are so soupy you could barely even see your hand in front of your face. Here's another picture. What an ugly, horrifying terrain. It's just dry slabs of volcanic rock. Notice there's no hills, no mountains, no pebbles, no rivers, no valleys, none of the shit that makes Earth so fascinating. It's just a hellscape. And it's been baked dry. We think that even though Venus has a thin lithosphere, there's so little water here that it basically just baked it into a solid lithosphere. No tectonics can really form. So it's interesting that one of the reasons why Earth has this cool dynamic geology is because of water. Water is like not just the secret to life, it's the secret to cool planets, right? I think that's an interesting thing. Okay, Andy, take a moment to grab this, and then I'm going to give you 3 bullet points on erosion, and then we're going to take a break. But I'm going to keep this erosion painfully short. I just want to have something in there. And let me
I'm
know.
all set.
Yep, let me know when you're good, Andrew.
I'm all set.
Okay. So let's erase this. We'll do one more quick module, then we're done. Okay. I think of basically 4 things when I think of erosion. To really fully understand erosion, you're going to have to wait till next week until we do planetary atmospheres. But there's a few things that we can say. Erosion reshapes the surfaces of planets on a very, very fast time scale. It's the fastest of all the geological processes. Reshapes a planetary surface over relatively fast time scales. Hell, a footprint made in the mud probably will only survive a couple of days. Mountains can get worn down in hundreds or thousands of years. There's basically 3 forms in the terrestrial zone. There's wind, there's water, and there's ice. How many of these depend upon having a planetary atmosphere? Which of these could I have on Mercury, which has no atmosphere? Which of these could I have on the moon, which has no atmosphere?
All right, so wind on the moon.
Not fucking possible, right? The moon has no atmosphere. Wind is gas blowing around, right?
Yeah.
What about water? Can you have liquid water without an atmosphere? No, you cannot. In space, water can take the form of ice or the form of gas. Water also needs an atmosphere. Apparently, you do see ice on planets without atmospheres. How much the ice moves around is debatable because the atmosphere also creates changes in temperature. I'm not sure that you can have any erosion without an atmosphere, except we do see some on atmospheric worlds. There's another form in the outer solar system. I hate to bring this in now, but in the outer solar system outside the frost line, we see this weird hybrid between water and wind and ice, and I'm going to call them frost jets. I'm not going to say too much about them now, but later on, you're going to see that there's a weird type of its own erosion called frost jets in the outer solar system. Now, for the most part, wind is a potent form of erosion, right? Wind will sandblast surfaces, creating hills and interesting structures. One of these structures that you'll famously see on the surface of Earth and on Mars are these weird hillocks caused by wind and they've got a funny name. They're called yardangs. So there's a new Scrabble word. Yardangs are wind sculpted dunes. We see yardangs both on the surface of Earth and on the surface of Mars. And before we stop here, I'll just, cue up a picture of what do you get if you type yardang. This kind of stuff is a yardang. This is a yardang. These are yardangs. Here's a classic picture. Stuff like this is a great example of wind erosion. Guys, I don't know if any of you spent time in the West, in the Southwest, but I was a Rhode Island kid that went to college at the University of Arizona, and I must have been 18, probably the age of some of you today, when I got on a plane and went out to Arizona for the first time. I had my suitcase with me, and I landed in Phoenix, and I got on a 3-hour shuttle bus to go down to Tucson. And I'm sitting in the back of the shuttle bus next to this old cowboy. He's got a 10-gallon hat and a bolo tie on. And all of a sudden, I see this thing out in the desert. I'd never seen anything like it in my life. It's called a dirt devil. And the first time I saw, sometimes they call them dust devils. But here's a picture of one of these things. And it looked just, I swear to God, just like this picture that you see here. So I'm in the shuttle bus with this old man, and I see this thing whipping across the desert. And I said to him, "Is that a tornado?" And he went, "No, that there son's a dirt devil." And I was like, "Well, what the hell's a dirt devil?" He's like, "I'll tell you what, that thing will take the skin off your face and the paint off your car. You don't want to get caught in one of those things, Sonny." And I watched this little mini tornado of dust just blast across the surface of the deserts out in Arizona. Now, if you grew up in Rhode Island like me, you maybe have never seen a dust devil. On the other hand, if like Joel, you've spent some time overseas in some Middle Eastern country, ever see things like this out in, were you in Iraq or were you in Afghanistan, Joel? I can't remember.
Afghanistan.
Did you see stuff like this out there?
So in 2013, I moved to Phoenix after I got out. And I was there for 5 years. And during, was this tsunami or no? What
El
what
Nino or
season
something?
do they have?
Oh, monsoon. They have monsoon season.
Monsoon, yeah. Everybody's like, oh, just wait until the sandstorms start. And I'm like, sandstorms?
I ain't afraid of no sand.
Towards the end of our tour, we had a real sandstorm. It came up over the hill. I mean, literally the whole horizon, this wall of sand came up and over, and it engulfed us for like half hour.
Was it scary?
Oh my God. It was like we're just like, we were outside until it like was like on top of us. Then we went inside. But like we had sand everywhere for like a month. It was crazy. It was the craziest thing I ever saw.
It'll mess you the hell up, right? Now, Joel, I've got something for you to consider. Let's imagine we took a trip to Mars. This will be my final picture of the day because I've overextended myself. I want to show you 2 images of Mars taken with the Hubble Space Telescope in 2001. And you got to keep in mind that these are 2 images that are like 1 month apart. And since you guys had that Martian lab last week, June 26th of 2001, you can see all those surface features that we studied last week, right? You can see
That's
like
crazy.
the Tharsis Montes, you can see the ice caps. Look at this, 1 month later. Do you see this? This is a planetary-wide dust storm. The entire planet at one shot can get covered in a huge giant sandstorms. Now, the atmospheric pressure of Mars is much lower than Earth's, so the force of the wind is not as strong as like Earth hurricanes can be. However, if you look at the surface of Mars, you'll notice, and I've got a couple of pictures here somewhere, all of the rocks on the surface of Mars look super, super sandblasted and chipped up, Like, here's a picture of the surface of Mars taken from one of our rovers. Can you see all those pits and grooves inside the rocks there? You can tell, like, they're not smooth pebbles like you find in a brook on Earth. These rocks have just been beat to hell by intense dust storms that have chipped and pitted away at them. That's why a rock on Mars looks very different. It almost looks like this porous sponge or something. It's been beat by stuff.
Almost looks like volcanic rock.
Well, it is volcanic rock, but the point is it's been
Oh, yeah,
seriously
that's true.
eroded by wind erosion. Now, there isn't a drop of water on Mars today. So there are no Grand Canyons carving. In the past, there probably was, but there are no rivers today that carve stuff out. There's ice on Mars, but it doesn't move around too much. Today, the main form of erosion on Mars is wind. If you think about it, in the terrestrial zone, Earth has active erosion, no erosion on Mercury, no erosion on Venus, and some erosion on Mars. Earth and Mars are the only two planets that have erosion. What's weird is when we get into the outer solar system, when things get really weird and creepy, you're going to see some forms of erosion outside the asteroid belt, and I can't wait to get there. However, for now, I think we've sort of covered our planetary geology as best we can for the day. We'll get back to more of it later. We got a big homework coming up today, so I want to give us a nice beefy break. Let's take until at least 1:15, maybe a little after that, and then we're going to do the Chapter 9, homework number 9. Does that sound like a plan, everyone? All right. Let's take a break for safety's sake, and I'll see you guys in a bit.
You want to record it?
Yeah, I just hit record so that the night class can see this. This looks awesome.
All right.
This is an Afghani dust storm.
Wow.
Freaking wall of dust.
Holy smokes.
Bro, how's it feel to see your death walking into
Yeah, I wasn't kidding.
Yeah, that looks like the whole sky is coming down on you there, huh?
Yeah.
Wow, Joel, that's amazing. And you can't stand out in that thing. It'll just rip your skin off, right? Or it'll hurt.
No, so this is the fastest that the Afghanis move. Yeah, it's not like terrible, but like it's just suffocating. But yeah, it more just like sucks all the oxygen out of your lungs because.
And you can't see very well, and yeah.
No, you can't.
So you went inside when that got to the base.
Oh yeah.
That's really cool, man. That's really cool.
Those are our senior guys, and they're just laughing at us.
And so that was probably the first one you'd seen, huh?
Oh yeah.
That's
Yeah,
a
there had
huge
been-
wall. That's crazy. Just like in the
There was-
movies or something.
Like you can't even like. It's so big because you can't even. Yeah, it's just crazy.
Well, what do you? Since I'm recording, since I'm on the clock here, what do you guys say we crank out this homework first? Let's. Thanks for sharing that, Joel. That was really cool and also kind of scary.
Yeah.
I believe we're doing chapter. This is homework 9, chapter 9, right? Let's just confirm that.
Confirmed.
Confirmed. And you got those numbers handy, Jake?
Yeah.
All right, hold on. Let me kill some background tabs, which ought to help with the. All right, keep those handy, Jake. I'm going to ask you to read them for me. Read the numbers, but let me get set up here. Okay, so usual homework business. Name. AS1010 with your section. This is homework number 9, chapter 9. And what do we got, Jake?
48, 55, 57, 59, and 60.
Okay. And Jake, while we're at it, if you'd be kind enough to read us 48, we can get going.
Sure. 48. Miniature Mars. Suppose Mars had turned out to be significantly smaller than its current size, say the size of our moon. How would this have affected the number of geological features due to each of the 4 major geological processes? Do you think Mars would be a better or worse candidate for harboring extraterrestrial life? Summarize your answers in 2 to 3 paragraphs.
All right. So we want to talk about how this would have affected Mars's 4 geological processes and what it would look like today. And then we want to talk about life. Let's remember that today, Mars shows a variety of interesting topographical features, from massive dead volcanoes and huge chasms, things that look like ancient river valleys but are no longer functioning, and then also some cratering. In fact, if you think about it, Mars kind of runs the gambit of the 4 geological processes, although not too much tectonics. But what if Mars had been smaller? What would the size of Mars have to do with any of these geological features? What have you guys learned? Why would the size of Mars have any bearing on the geology of Mars?
Professor, I could give it a shot.
All right, let's hear it.
So basically, the smaller the planet, the less time that the inner what would you call it? Like the asthenosphere.
We could just say the mantle, even. Just keep it simple, the mantle.
Yeah. So basically, it would basically die up faster than a larger
Wait, when you
planet.
say die, what property are we talking about? What physical property?
It would cool off.
It would cool
the inside.
off faster, right?
Yep.
And so how would that affect? Okay, so that's the first thing. The smaller the planet, the quicker it cools off, the thicker its lithosphere will become, right? And so what then?
So when it cools off on the inside, the convection actually will stop.
Correct?
And once the convection stops, the volcanoes will cease to form.
Right. So instead of seeing Olympus Mons, you'd see nothing, right?
Or a much smaller version of it.
I suppose on the moon today, we do see volcanism in the form of Maria. So maybe there might be some lava pools that are dead or left behind. But yeah, we wouldn't see no Olympus Mons, would we?
No.
What about Valles Marineris? Would we see that?
Well, if there was no volcanism, then there would be no pools of lava to form. So no.
Yeah, and remember, Valles Marineris probably started off as a tectonic feature. Probably the pushing up on the lithosphere fractured this crack, but then you can clearly see that at some later date, it was probably flushed out by water, right? Because if you follow the Valles Marineris down here into this channel, you can start to see what look like serpentine rivers. They're all dry today, but this is on Earth, the Grand Canyon was completely erosional. But on Mars, this probably started off as a fracture in the lithosphere, like you can see over here in the Noctis Labyrinthus. And then it started to fill up with water and just flush the whole thing out. You wouldn't see any of that. There'd be no more tectonic features like the Valles Marineris. There'd be no more river valleys. What would you see? What would you see instead? Was that Andrew? Who was I talking to there? What troll was I speaking with?
Oh, this was Andrew, that troll.
Okay, so Andrew, so
So-
then what would I see?
Oh, I'm not sure exactly like the question that you were asking.
Okay, well, right now, you told me what will not be there. But obviously, this mini Mars won't be a featureless ball. What features would I see on the planet?
Just impact craters.
Yeah. The dominant geology that you'd see would be impact cratering, because the planet would still be getting hit. Impact cratering is the default geology that you get when there's no other cool geology. Now on the moon, we do see some Maria, so perhaps there might be some Maria, but you wouldn't see any of this craziness. No more volcanoes, no more channels, no more dried up rivers, no more northern hemisphere ocean, none of that. So let's write that down. If Mars had formed smaller, say the size of our moon, the number of interesting geological features, and here interesting, I'm kind of use loosey-goosey, but whatever. Features we see today would have been greatly reduced. That's the big picture. If Mars had formed smaller, say the size of our moon, the number of interesting geological features we see today would have been greatly reduced. Firstly, a smaller Mars would have cooled its interior much more quickly, resulting in a thick, impenetrable lithosphere. We'll just say resulting in a thick lithosphere. The lack of internal heat would prevent the formation of volcanoes and tectonic features. Gone, I'm going to do some Yoda speak here. Gone would be the massive shield volcanoes of the Tharsis, Montes plains, and the Valles Marineris would likely not have formed. So I'm just adding in a few, cultural details here, just saying that I understand the surface of Mars. I'm going to have to hit return and go back up to the top here. So let me give you guys a second to catch up. Andrew, what part are you on right now?
The tectonic.
So I could erase maybe the first 3 or 4 sentences.
Yeah.
All right. Hopefully no one else minds if I just kill this stuff up here. So we'll continue on and say, without volcanic outgassing an atmosphere would not have formed, and no liquid water would have condensed to the surface to form what are now dried riverbeds, or maybe even ice caps. Although that's
Wait.
debatable because we do occasionally.
I'm confused on the word. What is that? Thereus? The what?
I'm sorry, where am I here?
Down there. The theory monks. What's that?
Oh, that's Tharsis Montes. Real quick, let's make sure I spelled that right. This plain is known as the Tharsis Montes plain. THARSISMONTES. My handwriting isn't so great. The Tharsis
What
Montes.
is it?
MONTES.
Oh.
Like Monty Python. Okay. Instead, you would have an airless rock pitted with even more impact craters. And maybe Maria. We'll throw it out there. In short, a mini Mars would more closely resemble the moon. I'm going to erase one more sentence here. And therefore be an unlikely place to find life. Okay, that was a very complete answer there. Whew. Boy, my handwriting's kind of sloppy today. Really damn sloppy. Noah, Andrew, let me know when you guys are done so I can move forward. Noah's good. So that was pretty well done, Andrew. You got to the point right away.
All right.
Are you good, Andy?
I'm still writing.
All right. Okay, let's erase this up. Yeah, Arizona has some of the most diverse topography of any state. You can go from forests and mountains to deserts in a matter of under an hour. You know, it's crazy.
Yeah, my sister lives up there, so when we go driving, the highway is always like all you see is like the mountains, 360 all around. Like there's always mountains.
I remember that. Yeah,
There's a
being in
lot of
Tucson, rings of
Native
mountains.
Americans area like very blocked off and everything. So
Yeah, there's so much cool stuff out there. I remember once I took a trip up to Phoenix, and outside Phoenix is a town called Chandler, and I saw these ostrich races. You were like sitting in a stadium drinking Budweisers with a bunch of cowboys, and and these like farm girls come out in like 44-gallon oil drum chariots attached to ostriches, and they race around and like have crash up derbies. That was completely wild. I'd never seen anything like that. Anyways, Joel, how do you feel about reading us 55? Are you into that?
I suppose I could do that.
Okay.
Surface area to volume ratio.
Now, let me say something. The book wanted to frame cooling of planets as a surface area to volume ratio. That's a little awkward because it's proportional to 1 over the radius. I thought instead we're going to make a modification, Joel. We're going to call it the volume to surface area ratio. And this is a quick and simple little problem. Remember from our lectures last class, the volume to surface area ratio of a planet goes as 1/3 R. So, okay, Joel, read us out.
All right.
Oh, by the way,
compare this.
I'm sorry, Joel, to do that too. The volume to surface area ratio is proportional to the amount of internal heat holding capacity of a planet. If you do surface area to volume, it's proportional to the cooling rate, but then it's 1 over radius, which is awkward. Okay, say it again, Joel.
All right. Compare the surface area to volume ratios of the Moon and Mars, part A. Part B is Earth and Venus. And in each case, use your answer to discuss differences in the internal heat of the 2 worlds.
So I can help us out from memory here. The surface area, the radius of Mars is roughly 3,400 kilometers. The radius of the Moon is roughly 1,700 kilometers. So let's set it up like this. The volume to surface area for Mars divided by the volume to surface area ratio of the Moon is going to equal 1/3 top and bottom, those are going to cancel out, times the radius of Mars is 3,400 kilometers over 1,700 kilometers. And as you guys can see, the 1/3 are going to kind of slash out, so we don't even need to compute them. You guys can just do 3,400 over 1,700 and tell me what you get. Like 1 sig fig. 2, says Joel. And Joel, what is the idea? What is the meaning of this 2?
So Mars will hold its temperature twice as long as the moon.
Something like that. Or maybe Mars has twice the internal reservoir of heat. It's something loosey-goosey.
Yeah.
So we'll phrase it as Mars
Has more heat holding properties or potential.
Yeah, a potential. Mars holds twice as much internal heat as the moon. And the next one was Earth and Venus, correct?
Yes.
So the volume to surface, hold on, let me restructure this. The volume to surface area ratio of Earth over the volume to surface area ratio of Venus. This time we're not even going to bother with the 1/3. We'll go as the radius of Earth to the radius of Venus. The radius of Earth is 6,400 kilometers. Venus is basically 6,050 kilometers, which is approximately equal to
1.8. No, I won't. No.
No.
1.08.
So basically 1, right?
Yeah.
Which means that Earth and Venus hold similar amounts of internal heat. And that, my friends, takes care of another problem. Problem 55 to be exact.
I can't see the bottom.
Does that help?
Yes.
Yeah, when I was in Afghanistan, Brendan,
Yeah.
it'd be like 110, 120, sometimes like close to 130.
Oh my God. And you've got all your gear on. I bet that's not a fun.
Yeah, wearing 80 to 100 pounds of gear.
Oh my
You know,
God.
in a monkey suit that doesn't breathe. Yeah, it's fun. It's fun.
Oh.
But yeah, when that sun goes down and there's like
All the heat just
zero
radiates off into space, right?
zero infrastructure to hold the heat down. And
Right, because
like,
without the moisture,
it's
the
like-
infrared, without the greenhouse gases, the radiation just goes right into space and cools super rapid, right?
yeah, so it drops down to like 80, maybe 75, but that's so, it feels so cold that like you're wearing like, there are some guys who are wearing like a fleece coat when it's like 80 degrees out. It's funny.
And probably the wind is whipping, which increases evaporation and makes it feel even colder, right?
No,
No.
it wasn't too much wind,
Oh, okay.
but yeah, it wasn't bad, but it was like It
Bet the
was
stars looked good though.
literally night and day. Oh yeah, yeah. I've got pictures of the nighttime, and the moon. Like you see the moon here. It's incredible.
Right. It's just so bright, right? It's yeah. You know, I really love Richard Burton's Arabian Nights, like the 1001 Tales of the Arabian Nights. And when they talk about a beautiful woman in the Arabian Nights, they say she had a face like the full moon. Like to them, that would be like the highest compliment of beauty. If you have a face like the shining full moon, then you are a beautiful woman. And I thought these are people who really appreciated the moon.
Yeah.
How we doing, Andy? You got all this yet or what?
All set.
You're all set? I'm going to erase class. Any objectors? Or okay, chapter 9, number 57. Jake, you're next to my Hollywood Squares. You down to do some reading?
Or
I think
alrighty,
this might be the big whopper. This might be the footprint one. We'll see.
perfect. Lunar Footprints.
Okay, now, before you start, Jake,
Yeah.
for us to really enjoy this problem, and I put that in quotes, okay, you need to see a picture to understand what's going on here. So let's land on the moon together, okay? Let me see if I can find this thing. One small step for man, one giant leap for mankind. Okay, here we are on the moon, and we step out of the the lander, and you guys will notice that there are footprints in the lunar dirt. They were just shocked to discover the entire surface of the moon, every square centimeter, had been ground and pulverized into a fine silicon powder, which we call the Lunar Regolith, aka moon dust. The entire surface of the moon is covered in several centimeters worth of magical moon dust. And we realized that one of the reasons why the moon is covered in this regolith, or 3 or 4 centimeters of moon dust, is if you're on a world that has no atmosphere, every little pea-sized grain of rock and metal that comes flinging through the solar system, instead of getting sort of burned up in an atmosphere, every tiny little pebble strikes that ground and creates a little meteor crater and grinds up the surface of the planet. And because the smaller the impactor, the more frequently they hit, there are literally millions of little grain-sized pebbles striking the moon every single day. Over hundreds of millions of years, it has ground the entire surface of the moon up into this dust. And it actually became a problem during the Apollo mission because they were tracking the silicon dust into their lunar module. And just like Joel was saying, it's hard to breathe in one of these sandstorms. They were having trouble breathing inside of the cockpits because of all the silicon dust getting kicked around, which was probably really scary. Anyways, go ahead and Jake, let's consider how, by the way, this question is about Neil Armstrong's boot print in the moon. That's the idea, okay? So go ahead and read it out for us, and I'm going to draw a picture for you of the moon on the right here.
All right. Lunar footprints. Assume that the moon is hit by about 25 million micrometeorite impacts each day. This number comes from observations of meteors in Earth's atmosphere, and that these impacts strike randomly around the moon's surface. Also assume that it takes about 20 such impacts to destroy a footprint. About how long would it take for one of the footprints left by the Apollo astronauts to be erased? Hence, use the moon's surface area to determine the impact rate per square centimeter and estimate the size of a footprint.
Okay. Let's start by drawing a sphere that represents the moon. And let's draw the radius of the moon, which you guys know is about 1,700 kilometers from our previous problem. And somewhere on the moon, let's draw Neil Armstrong's boot print, okay? Now, although they wanted us to figure out the number of impacts per square centimeter, I thought this could be a cool opportunity for us to think about the problem from the point of view of probability and gambling, and also darts, which are all things that humans like to do. We can sometimes model these problems with what is called the Monte Carlo method in statistical analysis, named after the famous gambling resort. The idea behind the Monte Carlo method is we're going to assume that there is a random computer or a robot who is throwing darts at a dartboard that is the moon. And the only condition is that we program the robot such that every meteorite dart has to fall somewhere on the surface of the moon. But as long as it's on the moon, it'll fall completely randomly. It'll be in a different spot each time. And if we throw 25 million darts per day, we're trying to figure out what is the probability that just one of those micrometeorites would actually hit the footprint. This is called a Monte Carlo simulation. Now, let's first work out in our mind what the probability would look like. And as a way of doing that, let's supersize our footprint in our mind. And let's imagine, students, what would the probability be if Neil Armstrong's boot print was so big that it had covered 1/4 of the moon's surface? What would be the probability that one micrometeorite would strike the footprint?
One in four.
1 part in 4, because if it's going to fall randomly around, there's a 1 in 4 chance it will hit this quadrant, right? And let's think about how we structured that, Joel. We said that the probability of a single dart hitting the footprint is essentially the area of the foot divided by the area of the moon. Since the area of the foot was 1/4 of the moon, it was a 1 in 4 chance. But the same logic should hold even if the footprint gets smaller. If the footprint is 1/8 of the moon's surface, there's a 16% chance. If it's 1/10 of the moon's surface, then there's a 10% chance, right? Yeah. Jesus, where's my mind? What do you think the area of a foot is in square centimeters? I got an idea. Let's get ourselves a boot. Okay. Hey, look. The Army Navy surplus store in Thayer Street is going out of business. That's a sad day because I've been going there since I was a little shaver. But I got myself some cheap $30 hardcore goth combat boots. It's kind of similar to a moon boot, maybe. Let's see, how many centimeters, roughly how many centimeters long would you guys say this boot is?
30.
Yeah, 30. And how many centimeters wide would you say it is?
10.
Okay. So let's imagine a rectangular boot. A rectangular boot that is, so here's our boot. Our boot is 10 centimeters by 30 centimeters. We'll approximate it as a rectangle. And that means if it's 10 centimeters times 30 centimeters, we're going to have 300 centimeters squared. Now we have to divide it by the area of the moon. The area of the moon is 4 pi times the radius squared, but we have a problem. Our radius is in kilometers. What are you all going to do about that?
Dimensional analysis.
At
Dimensional
6
analysis
zeros.
How many?
6, I think.
Not 6, Noah. What is the conversion from
Oh
centimeters?
wait, 4, 5.
5.
5. Okay. I was about to say, this porridge is too hot. This is too cold. So Noah, I'm going to teach you a slick Rick trick that you can use on the exam, a fast conversion from kilometers to centimeters. We're going to divide by 4 by pi. And here's how I'll sometimes put it into my calculator. I would actually do 1,700 times 10 to the 5 centimeters squared. That's a way to convert it without having to actually stop and convert it. And let's try punching that right into our calculus here. So 300 divide by 4 divide by pi divide by 1,700 exp5 square equals. What do you guys get to 2 sig figs? What y'all get?
(1.4 times 10 to the negative 7).
False. You forgot to square.
Poppycock.
Anybody else? Calculating is a you job. Don't forget. I just work here.
I got 7 to the times 10 to the negative 8.
Oh God, guys, you're all fired. You're
You want
not on
2
my
sig figs?
2 sig figs.
Oh, 7.0? I don't know.
No, you
8.3 times 10 to the negative 16.
There we go. There we go. Joel, what does that number mean? That tiny, wicked tiny number, what does it mean?
That is that's the probability of one of the meteor things hitting the footprint.
Right. Which looks like a pretty effing small probability, right?
So 15 zeros, then 8-3.
Right. Obviously, that's a pretty tiny bullseye. Now, probabilities don't have units inherently. A 25% chance is just 0.25, 25% chance of happening. But if we want, we can actually assign some goofy units here. I'm going to assign this as the ratio of, let's call when there are moon strikes and then there are foot strikes, or moon impacts and foot impacts. This is the ratio of foot imps to moon imps. Those are the units that I'm going to make up. Since they're both imps, since they're both impacts, they will divide out, leaving us no units. But there's a difference between a foot impact and a moon impact. Anyone have any ideas about how we might proceed from here? It's not a very high probability. On the other hand, we got a lot of impacts. Are those foot impacts or moon impacts?
Impact.
Sorry, Jake?
Moon.
These are moon impacts. Jake, based on the units, moon impacts per day, can you suggest a method by which I could find the number of times it hits the foot per day? Based on dimensional analysis? How about I use dimensional analysis to find the number of foot impacts per day?
Sure, if you want.
No. I'm asking you what to do.
I guess. I don't know. I thought we were done, so.
They want to know how long it will take to destroy the foot. That was the question. That is not a time. That is a probability. That's not done. We're not done until we find out how long that footprint will sit on the moon. Okay. Jake, I don't think you understand what I'm asking you to do. So let me
I
spell
mean,
it
I
out.
know what you're asking. I just don't know like how to do it.
But you would if you just think about units. I want you to take the numbers on the screen, multiply and or divide them in such a way that you get a number whose final units are foot impacts per day. Do you think you could do that?
I mean, I think I know the numbers to do it with.
No, no, no. I want the units. I'm more interested in the units. Tell me the units. That's what it's all about, buddy.
Units would be moon impacts per day.
Okay, so let's over here. Let's put moon imps per day. And then what goes over here?
Just moon imps or foot imps.
Well, I need to end up with foot impacts per day. So you tell me. See, this is your job. If you have moon impacts per day, what needs to go there to get foot impacts per day?
I'll guess foot imps.
Just
Take
foot
your
imps.
answer.
Top or bottom?
Take your
Bottom.
Now your units are moon impacts per foot impact per day. That's not what I wanted. I do not want I do not want moon impacts per foot impact per day. I want foot impacts per day. So try again.
So moon impact on the bottom.
Okay, and what goes on top? If you put moon impacts on the bottom, moon impacts cancel with moon impacts, and then you have per day. I do not want 1 over days. I want foot impacts per day. So keep going, Jake.
So foot impact on top.
That's right. I want to multiply it by the number of foot impacts per moon impact. Oh shit, look, I have that. Foot impacts per moon impacts are there, and moon impacts per day are there. So here I should do my 25 million, and there I should do my 8.3 times 10 to the minus 16. So multiply those two numbers and tell me what I get.
Moon impacts cancel out. To the -8th.
I'm sorry, say that again.
2.1 to the -8th.
You mean times 10 to the -8, right?
Absolutely.
Okay. 2.1. And that's foot impacts per day. Jake, what does it mean if I have 10 to the -8 foot impacts per day?
It would be 7 zeros in front of the 2-1.
Okay, true. But what does it mean that the number is less than 1? What if you had gotten 0.5 foot impacts per day? What would that mean? What if the number was easy? What if it was 0.5 impacts per day? What would that mean?
There's half a chance it would hit the foot a day.
That's right. Half a chance it would hit the foot per day, or rather it would hit half a foot per day. How many days would it take to hit a whole foot?
2.
Which you got by doing 1 divided by 0.5, correct?
Sure, yeah.
That's, I mean, if it's half a foot per day, you will hit an entire foot in 2 days.
Yeah,
how many days would it take?
How many
days would it take to hit a foot impact here in reality? How would I figure that out? See, Jake, I don't want the number of foot impacts per day. What I really want are the number of days per foot impact. So how do I get that number? How do I figure out the
So
number
you
of,
have to do more dimensional analysis.
yeah, you have to do more dimensional analysis. So how do I turn foot impacts per day into days per impact?
You would have to times by day over foot impact.
Then you would get units of nothing because days would cancel with days and foot impacts would cancel with. You need to do something simpler, Jake. You have foot impacts per day. You want days per foot impact. What do you do?
Flip them.
That's right. You flip them.
Oh,
And that's called taking the mother effing reciprocal. Okay.
sure.
Because you need to equal 1, Jake.
1 divided by 2.1 times 10 to the minus 8 will give you units of days per foot impact. And what is that, Jake?
Isn't it just 2.1 times 10 to the negative 8th?
No. Could you please put it into your calculator like a real man?
Well, I got like a huge number, so I don't know if I did that right.
Well, should it be a short number of days or a long number of days until you end up hitting the foot?
Oh, long.
Well, then that sounds good. What's your number?
497,512.
I don't believe you.
That's what I mean.
I mean, all you've got to do is hit your reciprocal. Oh, yeah. Wait, it's not. Count better. You suck at counting zeros, okay? Do it better.
Oh, wait. Oh, no.
Hey, feel free to help him, guys, you know?
Yeah, Jesus Christ.
I got 48 million.
Thank you. See, Noah talks to me the way I want to be talked to here, okay? It's convince yourself, Jake, that that number is 48 million. There's 1, 2, 3, 4, 5, 6 zeros, and then you get to 47.6. So it's 48 million days per foot impact. How many impacts does it take to destroy the foot?
Twenty.
20.
So what do I do next? I'm going to erase this part.
I would do 20 times that amount of days.
Okay. So 20 foot impacts times 48 million days per foot impact. $20 times 50 is what, 1,000?
960. 48 times 20 is 960.
You're good at that, son. So 9.6 times 10 to the 6, 7, 8 days.
Yeah.
Is that right?
Yeah.
How many years is that? What's the conversion, days to years? I'm going to erase this
Right.
bottom row. I guess Andy
One
left.
year, 1 year to 365.
Okay. What do you get?
2.6 million years.
That's how long Neil Armstrong's boot print will stay at the surface of the moon. How long would Neil Armstrong's boot print last if it went down in your backyard in Rhode Island?
Couple of days, maybe.
Couple of days before it washes out. This makes you realize what a powerful force erosion is. There is never a gust of wind on the moon. There is never a drop of rain. There are no rumblings of tectonics. There are no paving over. It just sits there in the vacuum of space until little grains of sand pick them away. A million years from now, this thing might look a little beat up, but it's still going to be there. The surface of the moon is truly stagnant geologically. There's your final answer. That was the hard problem today, but as you see, it's not an uninteresting problem. Okay, I'm ready to erase and move on when you gents are. Noah? All right, here I go. Last two problems are pretty straight up. Noah, you want to read us 59?
Yeah, give me 1 second. I gotta pull it up. All right, internal versus external heating.
Okay.
In daylight, Earth's surface absorbs about 400 watts per square meter. Earth's internal radioactivity produces a total of 30 trillion watts that leak out through our planet's entire surface. Calculate the amount of heat from radioactive decay that flows outward through each square meter of Earth's surface. Your answer should have units of watts per square meter, and then compare quantitatively to solar heating and comment on why internal heating drives geological activity.
So in one sense, we have sunlight beating down on Earth. The sunlight delivers us 400 watts per square meter. On the other hand, inside the body of Earth, you'll remember that planets are heated by radioactive decay, by those little isotopes that pop off. And they're estimating, I'm sorry, was it 30 trillion watts, Noah?
Yeah.
And all they're trying to ask, Noah, is once those 30 trillion watts leak their way up to the surface, how many watts per square meter will be coming off the surface just due to the internal radioactivity? And just to save us some time, this looks like a job for the inverse square law. The brightness at the surface will be the luminosity, which is the 30 trillion watts, or the power, divided by the surface area of Earth. The radius of Earth, of course, is 6,400 kilometers. If you guys can tell me how many meters that is, we can speed this game up.
6,400,000.
Yeah. So 3 zeros makes it 6.4 million meters, right? Use dimensional analysis if you can't do that. So we're going to plug this right in, and we'll get a brightness of 30 times 10 to the 12 watts over 4 pi times 6.4 million meters squared. Sounds good.
I got 370,000.
You need to divide by 4, divide by pi, divide by that squared. Your number's too high, Noah.
No, I got 0.05.
Yeah, and the units?
That would be watts per meter
Squared.
squared.
The square distributes the meter as well. And this, Noah, is the amount of geothermal energy that's leaking across our lithosphere.
Sorry,
So-
it was 0.06 actually. I rounded wrong.
Okay, all right. What's the second part of that question?
Compare quantitatively to solar heating and comment on why internal heating drives geological activity.
This is a bit confusing, guys. 400 divided by 0.06. Let me do that for you. Is 66,000 times less than solar heating. Class, what do you think drives geology on Earth? Internal heat or sunlight?
Internal heat.
Internal heat is what we learned. And yet, Noah, you just calculated that the internal heat flowing across our lithosphere is 6,000 or 7,000 times less than solar heat. Why aren't volcanoes being triggered by sunlight? Why aren't volcanoes, earthquakes being triggered by sunlight?
Well, that's solar heat. Is that like from the surface of the sun, like in all directions?
No, that's what we receive at Earth. In all directions, it's 4 times 10 to the 26 watts. We only get 400 by the time it gets down to Earth. This is supposed to be a confusing answer, Noah. We expected what you just said is geothermal energy should drive geology, yet it's way wimpier than sunlight. So what's up with that?
Does it have to do with Earth's gravity?
No, gravity doesn't
the-
affect
or-
sunlight.
Is it because the
Or the
sunlight rays
atmosphere.
come to us in UV?
The 400 is bolometric. It includes UV, visible, and infrared.
Maybe none of that gets below the crust?
That's it, Noah. Very, very good. See, this energy only penetrates a centimeter too. It's about entropy. It gets re-radiated into space. But even though this is a lot wimpier, that's the energy that's flowing across the crust through conduction. You got it, dude. Let's add a sentence about that, okay? That was a trick. I did not expect any of you to get that, so I'm very impressed. Okay. Even so, geothermal energy drives geology. Because it flows across the lithosphere via conduction, whereas, nice use of whereas there, whereas sunlight is re-radiated back into space. You guys good?
I'm good.
I can move as fast as you guys do.
Give me a second.
All right, sure.
All set.
Okay, any other objectors before I erase this beast? Last problem's a real cinch, too. Joel, I'm going to ask you to read 60 again for us.
All right.
We lost Andrew.
So 60 is plate tectonics. Typical motion of one plate relative to another is 1 centimeter per year. At this rate, how long would it take two continents 3,000 kilometers apart to collide? What is the global consequences of motion like this?
What did they give us for velocity again? My
1
South America
centimeter,
ain't looking so good.
1 centimeter per year.
Oh, I'm pointing in the wrong direction. That's why. Whatever. One centimeter per year?
Yeah.
And we want to know how long. How long means time. How do we get time if we have distance and velocity?
Divide distance by velocity.
Yeah, if distance is rate times time, time is distance over velocity, which is 3,000 kilometers divided by 1 centimeter per year. How do we deal with the units here? Hey, Noah, what's the conversion from kilometers to centimeters?
10 times 10 to the 5th.
So if we multiply by that, that ought to get us there. Actually, I don't even think you need a calculator for that, do you, Noah?
No, you're just gonna add 5 zeros to the end of that.
Okay, so do it and tell me what it is.
It'd be 3 times 10 to the 8.
Which is the same as 300 times 10 to the 6. And the units?
Oh, just years?
Yeah, centimeters cancel, kilometers cancel. Bottom of the bottom goes to the top, years. And then what's the second part of that problem, Joel?
Well, let me copy that down. So 300 times
300 million
10 to
years.
the 6. That's not that long.
Well, compared to a galaxy, maybe, but compared to
Won't
us.
last that long. All right. So what are the global consequences of motion like this?
So what does it mean if two continents will come together or separate in 300 million years? Something simple, something big picture. It means every 300 million years, we can expect
Continents to bounce off each other?
yeah. In other words, this is the time scale for plate tectonics to basically just reshape Earth. 300 million years ago, you didn't look like this on Earth. it looks like Pangea. 300 million years from now, a child looking at a globe would not recognize. If this globe could take a time travel 300 million years into the future, whatever hyper-intelligent robots, Terminators that will have wiped us out, or whatever they are, like nanobots or gray goo, they wouldn't recognize this as Earth because it won't look like this anymore. So let's write down the following statement. This defines a so-called geological time scale over which plate tectonics will reshape the surface of Earth.
Angle down. So how far is Alaska from Russia?
There's a tool on Google Maps where you can calculate it, but according to my, I mean, at some parts, there's only a few kilometers that separate them, right?
Yeah.
According to Sarah Palin, you can see it from the window of her house, but I don't know. I don't know if you guys remember that, but
She doesn't live that far west.
as silly as she is, there's a point to that, which is there is an island that actually straddles the boundary, but it's like Russia on one side of the island. No, there's two islands, two little islands.
Yeah.
Families that live on them, and it's like you're in Russia if you're on one island, in the US if you're on the other. The Bering Strait was a real thing. That's probably how people got across hundreds of millions, or yeah, tens of millions of years ago, I guess. Maybe millions of years ago.
I didn't finish copying that down. Can you?
Oh, yeah, sorry. And that concludes homework number 9, my lovelies. We learned quite a bit today.
Brennan, is that an E or an O on the distance?
Here?
Yep.
It's an E. I should have just put V for velocity, but how about that? How you doing, Bella? You got all this?
Yeah, I took a picture of it, so.
Oh, I'm sorry. I don't know if you need more time or.
No. I just wanted to know that one part, but no, I took a picture because I know, like, I took your class last year, so I already know how you are with note taking.
Well, yeah,
It's faster.
it's important to get all these tidbits down because this will be a study guide for you before the exam, right? I want you to have all these books. Okay. Should I stop the video now? Do we have everything? Anybody need anything else, or can we call this meeting adjourned? Great hanging with you as always. I'll see you guys next week. We do have class Monday and Wednesday. Is next week Thanksgiving? Can someone remind me? Wow. Okay. Time's a flying. So we will have class Monday and Wednesday next week. Thursday and Friday are off. So I'll see you guys next Monday, okay?
Okie dokie.
Peace out.